One of the pillars of a green future is electric power. So by 2030, many thousands of specialists and managers are needed in the battery sector in Europe. To prepare us for this task, we created a place to train these experts, our ELLB. Here, we empower battery experts with leading-edge knowledge to shape Europe's green future. ELLB, European Learning Lab Battery Cells, part of the Fraunhofer Research Institution for Battery Cell Production FFB.
Good afternoon and a warm welcome to our second live battery webinar presented by the European Learning Lab Batterycells as a part of the Fraunhofer Research Institution for Battery Cell Production FFB. My name is Michael Wessels. I am the Group Manager for the Academy activities at the Fraunhofer FFB, and I have today's honor to guide us to the following lecture. A few weeks ago, we already got some first insights in the European battery ecosystem and an overview of the main battery markets, key players, and the cost drivers in the battery cell production. Today, we are going one step further and we are taking a short journey through the material cycle of lithium-ion batteries. But before we start with our speaker presentations, I'd like to give you, and especially those guests who missed the last lecture, a small overview over the Fraunhofer FFB and the European Learning Lab Batterycells, ELLB. Also, I'd like to present the webinar program and today's speaker, Dr. Gwen Giffin and Dr. Julian Schwenzel. The Fraunhofer FFB is located in Münster. It is an open battery cell factory for research and development purposes, which claims to become the center of development of a modern and scalable battery cell production for Germany and Europe. This claim is also fixed in our value proposition called Innovations for an Efficient and Sustainable Battery Cell Production. To ensure that production in Germany can provide new battery technologies more efficiently, more cheaply, and in the highest quality in the future, the federal government and the state of North Rhine-Westphalia are funding the research factory for battery production with a total of 680 million euros. The factory will provide infrastructure for small and medium-sized companies, but also large companies and research institutions can test, implement, and optimize the near-series production of new batteries with a theoretical yearly production capacity of up to 7 gigawatt-hours for electrode material. In addition to those technical supports for the upscaling of battery cell productions in Europe, a further aim of the Fraunhofer FFB is the transfer of battery knowledge to close future skill gaps. This is why the European Learning Lab Batterycells was established. The demand of the ELLB is to empower battery professionals with leading-edge knowledge to shape Europe's green future. The responsible project team for this task unites the competence of 5 different Fraunhofer institutes, the Fraunhofer Academy, and also the Fraunhofer Alliance Battery, and ensures that everyone will find the right course and lots of knowledge on the subject of batteries. The targeted philosophy is characterized by the following claims. We focus a close cooperation with relevant European players. The development of our curriculum will be marked by the iterative exchange with industry partners and also with an agile approach to address changes in the market and quickly create added value. We will include our industrial production lines, for example, through augmented reality applications and offer virtually interconnected smart learning. We will also add innovative possibilities in training and curriculum and also innovative learning environments based on the new work principle. Our first program on the market is the webinar series, which provides a short overview of these 4 topics. As already mentioned, we started with an overview about the European battery ecosystem. For all of you who missed this webinar session, there's good news: you can find recording on our website soon. Today, we will give you an insight into the material cycle of lithium-ion batteries, the challenges that come along in the process of production, and an overview of recycling. In the third webinar, Sustainable Battery Cell Production and Digital Twin, in March 2023, we will discuss sustainability issues in the classical lithium-ion battery cell production, as well as the use of digital twins. And last but not least, the forecast of the battery value chain regards the political, strategic, economic, and social challenges arise in the future when establishing the battery value chain. This webinar is dated for end of March 2023. All these topics can be intensified by our second program, the Pre-Charger Workshops, which will deepen the topics in practical seminars present in Münster. This program starts in April 2023 and is open for pre-registration on our website. Feel welcome to visit and check out our homepage and courses for more information and further booking options. For today, our focus will be on our second webinar. Our two experts, Dr. Gwen Giffen from the Fraunhofer Institute for Silicate Research and Dr. Julian Schwenzel from the Fraunhofer Institute for Manufacturing Technology and Advanced Materials, took a deep dive in the material cycle of lithium-ion batteries and had a look on different key questions for us. In the next hour, we will learn about the main materials, components, critical resources, challenges in the production process, and also the main application of lithium-ion batteries. Further, we will have a close look on next-generation batteries and alternative technologies. And in conclusion, we are dealing with different battery recycling technologies and have an outlook on future design for recycling approaches, which will be rather important. Afterwards, if you're interested, you're very welcome to join us for another 30 minutes for question and answer with our experts and enter the discussion. If you like to address questions in the ongoing presentation, you can use the chat function in Teams. All your questions will be saved and answered, at least in the following Q&A session. I wish you all a good time and I hope you will enjoy today's webinar. I'm now passing on to Gwen and Julian. Thank you.
Yeah. Welcome. Thank you very much. We now, in the next some minutes, would like to give you a short introduction about the lithium-ion battery technology, which starts like with this. So the energy storage plays a very important role in our applications, also in the future applications, especially in the batteries are in our daily life available, and they underlying different kind of requirements and different kinds of challenges. For example, energy storage will be necessary maybe for explanation for the stationary application. Also, if you would like to use renewable energy seas for villages or for houses, so you need also some energy storage technology to compensate the fluctuating energy. Also, if you would like to have portable or wearable devices, so they also need batteries, some energy storage technologies, which different kind of size, but especially it should be very flexible or small. Or if you look for electrical flying, it's a very new future challenging thing. And here is the question about the energy density, but also the weight. Also, the battery or the energy storage technology should be not heavy enough. Or the electrical mobility is also very important energy storage. And here's also the questions, how big is this battery and how many places or space you need to put the battery inside. So there are different kind of requirements, but also the temperature stability is very important. Also what kind of environmental infrastructure will be there, the lifetime, and also the safety and costs are very important. Also eco-friendliness and sustainability. So there are different kind of energy storage technology available and possible, and we can classify it in different kind of, how to say, in application scenarios. What is shown here on this axis, you can see the capacity, which means how many energy can you store in this technology. And on the y-axis, you can see the discharge times. It means how fast you can charge or discharge this kind of energy storage. So, for example, on the right side, there's power to gas. It's hydrogen. It's also very interesting. It's a big capacity, big energy, and also but needs also a long time to charge and discharge. This could be interesting maybe for more stationary applications, but also if we go very fast, one is for the capacitors or flywheels are also possible. But but batteries are the versatile compromise with respect to the capacity and the discharge time. What you can see here in green, and there are different kind of battery technologies available. This redox flow technology, lead acid, it's well known. Also the sodium sulfur system, but also lithium-ion batteries. And these are the most promising technologies with respect to the other battery chemistry. Yes, and but the history of this technology is very long ago, but the first developments was done in the year 1970. There was some investigation on maybe especially on this graphite materials, where they found that it's possible to intercalate lithium ions in these materials. But also 10 years later, there was other kind of developments in view of the cathode side. So maybe, for example, the lithium cobalt oxide material that was developed in the 80s, 90s, but only in 1990 there was the first device was developed. It was by Sony for camcorders, and they really create this kind of idea which you can combine this cathode side, maybe developed in 18, and this anode side which develops in the 90 together to develop the first lithium-ion battery. Since this was the starting point, and this lithium-ion batteries get much more applications and coming more and more power applications. So still today, it is the most promising technology where you are used in this different kind of applications, but still there's intensive research to improve their performance. How it works, this lithium-ion battery technology. So especially it's we call it rocking chair principle. That means the lithium ions are shuttled back and forth in between the positive cathode side and the negative anode side of the electrode. What you can see here in this scheme here. So on left side is the cathode side, and you have the anode side. And this electrodes here will be the energy storage, and here is really this happens where the chemical energy will be converted in electrical energy, and in this electrodes will really define the complete energy of this battery, and this is the product of the capacity what the electrode have and the voltage what this have. And so you can see in this formula, if you have a high voltage, which means a very low voltage in anode side and very high on the cathode side. So the difference will be the operating voltage, and also very high capacity, which means how many lithium you can store inside the structure will be given the energy. So the application will be really driven by need of higher gravimetrical and or volumetric energy densities. So there are a lot of kind of electrode materials available, and a lot of research will be happens here. There are a huge variety of compounds for anodes or cathode materials. This is what you can see here in the screen. So here we have the capacity of these different materials, and here is given the voltage that you can reach with this kind of materials. And the yellow and violet coloring here says it's more the cathode materials with a high voltage, and here down where the graphite or lithium metals, it's the anode materials. And the difference, for example, if we maybe use lithium cobalt magnesium oxide with 3.5 volt and graphite with 300 millivolts, so we can generate a battery working about 3.4 volts. So this will be the combinations that we can realize in a battery. But there's no best material setup since applications and specific materials, and there's a lot of research happening how to improve this in view of the capacity or improve of the potential. So the holy grail or the ideas will be to come in this region as very high capacity or high voltage. But what is a clear difference in this different kind of cathode materials what we are here? So the structure for this cathode materials is really important because this structure will define the capacity, the power, the stability, which means the long life cycle, and also the safety. So, which means we have different kind of structure of these materials. We call it olivine structure. This looks like this one. Also the green dots are the lithium ions, which can be placed in between the crystal structure. This is, for example, lithium iron phosphate. Or we have layered structure materials. Here is a layer, and you can see the lithium ions can really intercalate as a layer inside this crystal structure. And we have also the spinel structure. It's like this one. It's a more three-dimensional way, tunnels where the lithium ion can move in and out. So there are a different kind of materials available, and this cathode composition has an additional important factor for the performance, which means this kind of structure stability will really define the performance of this battery. Finally, the cathode materials can also described in different kind of properties. So you can here see this kind of diagrams where it's defined with the energy density, the power, the safety, the performance, the lifespan or lifetime, and the cost. And we can see how we can relate it. So iron phosphate, it's very interesting materials because low costs, have a high lifetime and or high safety, but especially about the capacity or energy density are not so lower in comparison to the lithium cobalt oxide systems. This is layer structures. So this shows a very high capacity and good performance. But if you see the lifetime, it will be not so comparable like with the iron phosphate system or also with the power. And safety is very also critical because we have here oxygen inside. And if you discharge this material too much, so you can initiate oxygen inside the system, and this will be a problem. Or we have another kind of layer structure material, all well known, the lithium NMC, lithium nickel magnesium cobalt oxide system with different kind of stoichiometries or with a different kind of mixture here. But this shows a very good high energy density, a high energy capacity, and also good safety and lifetime. And also the cost. So this is a very interesting material, which is really mostly used now in the most of applications. So the trends will be more in the higher capacity, higher voltage, low cost material, but also safety and sustainability should be very keep in mind here. So for this, the developments going in the question how we can reduce the amount of cobalt. As you know, cobalt is a very critical material. And here is can you see the developments from the last 20 years ago? So the cobalt content in this cobalt oxide-based cathode materials will be still going down. So, and what you can see is this NMC. This means the stoichiometry here, X, Y, Z. It means like this 111 or 622. So this is a composition. And if you look here, 811 means we have a high nickel content and a low cobalt content. So here it could be really reduce the amount of cobalt here. But then further other ideas with maybe cobalt-free system, this nickel magnesium oxide system are available in the developments. So the reduction of cobalt without losing the performance is a strong driving force in the developments for future lithium-ion battery technology. So if you now look for the other side, the anode side is also very important here. It's also some developments starting. So the state of the art will be the graphite. So graphite is economically attractive, but also a critical material. So the idea is really in development to exchange the graphite by silicon. Silicon is a well-known material, have a huge capacity, similar to lithium metal, but also shows a very high volume expansion, which means if you charge the system, also it's a silicon react with lithium, and so we have a high volume change, which will be also critical for lifetime or cycle stability. And finally, the holy goal, it's like this, is to use really the pure lithium metal because it's very light, it's a high capacity, but the pure lithium is very reactive and can formate dendrites, and this will be also critical to handle for shortcutting. So this is really the holy goal for the lithium metal to use here. But this is really a problem how to handle the reactivity and the dendrite formation. The materials and components and challenge maybe will also due to the materials what we are using here. And as you see here, that the demand of lithium-ion battery will increase more and more. Here's some forecast till 2030. That's a gigawatt hour per year. What is necessary will be more and more. And here it's very important to look really also in what kind of material will be used here. So the steadily growing demand of the raw materials. And so this should be also keep in view what kind of materials are used. And also about the safety. Also the inappropriate storage for usage of LIBs results in alkali aging. So this means the loss of capacity. Extreme temperature, wrong operation parameters or mechanical action can lead also for malfunctions. And the worst case, we call it thermal runaway, with the result of toxic gases and fire explosion, which means this have to be controlled via using maybe non-flammable electrolytes to control the heat what you have here and also to reduce the oxygen. And once you have the oxygen from outside from the atmosphere or also from the materials like here from lithium cobalt oxide. Good. So this was a short introduction about the lithium-ion technology. And if you have further questions, or
Hi, thanks, Julian. So we would now like to give the opportunity to you to have some input about what you think are the necessary innovations for lithium-ion batteries. As Julian mentioned, they're used in almost all aspects of our everyday lives, but clearly there are some future development steps that are needed. So what might those be? There are 6 questions. Please give your opinion about one of the answers, and then we can discuss those answers. So for example, do we need to work on higher energy? For electromobility, extending the range, of course, is something that most people are really concerned with. Is power going to be the main issue? Cost. Safety, we just mentioned here a minute ago, Julian mentioned about thermal runaway and issues associated with safety. Is this the key issue that has to be solved? Or is it something in the direction of more sustainability or eco-friendliness? Or finally, the last option, none of these are really the key point because clearly other technologies are needed needed as a complement. So now if you look on your screen, you should see a poll showing the answers that have been voted for the most. Clearly here, the answer towards sustainability and eco-friendliness is leading. This is something we will talk about later in the third part of today's webinar. Coming in at second at the moment is costs. Of course, this year in terms of cost, as you can see in the first webinar, as soon as it'll be online, cost hasn't gone down as much this year as was hoped in terms of the overall trends due to the increased raw materials costs. But hopefully this is something that may be solved in the future, maybe also with next generation technologies. The other answers then are more or less coming in higher energy, higher power, and higher safety with equal percentages. And finally, it's interesting to note that nobody voted for different technologies. This seems to imply that everybody thinks batteries are definitely going to be the driving technology for our energy change, and clearly is something we need to work on. I see now that the eco-friendliness aspect is over 50%, well over 50%. So hopefully then we can address some of these issues in the last part of our webinar today. So Julian, I will hand the floor back to you. And we can now start looking at next generation technologies.
Now I would like to give you a short view in the future. How is the development going? Maybe also to address this kind of challenges or kind of requirements what we are discussed now. So the most one of the most attractive way for more developments will be the energy, also how we can improve the energy density of these battery cells. So, and what you can see here is some historical view back now, starting from 1990 till 2015. As you can see here in red and in blue, the specific energy and energy density will be improved every year now, and we're going now maybe much more higher. Now, I think now in the year 2020, we are around 280 watt hour per kilogram now, as it's more improved here. And this was also mostly happened due to improved cell designs, which means the enhanced electromaterial and cell concept was improved, and also the optimization of the fabrication process, which means maybe how we can non-active materials less. This means how we can make thin separators or less packaging or less current collectors. Other technology how to improve it will be the all-state batteries. It's a very interesting technology because it could have a compact design, should be safe, and also have a high energy and power density. This will be also need a new process technologies, or also to use alternative chemistry. For example, maybe zinc, sodium, or metal oxide, or lithium sulfide. So it could also interesting technology for this. So I would like now to give you a short introduction about this solid state technology. What means it? This means that really exchange the liquid electrolyte with a solid electrolyte. And so if you can exchange this, and the solid electrolyte have a lot of opportunities and a lot of good properties here. For examples, you can use, for example, lithium metal as anode to use it safe, and then you can increase the energy density. Solid electrolyte is also not flammable. So liquid electrolyte is used by solid one, so you also can increase the safety. And also the thing is, the solid electrolyte have mostly is a single ion conductor. That means you have only the ions who can move, no anions, no electronic leakages here. So you can also increase the power of this technology. There are different kind of solid electrolytes available and under investigation. So we have now 3 classes of solid electrolytes. One of this class are called sulfides. Sulfides are very attractive because it shows very high ionic conductivities. So it's possible also to make it thick enough. No, it's for handling and also stable films. But the disadvantage will be with sulfides that they are not stable in air. So you need a special atmosphere. Additional high processing costs will be improved because you need something like dry rooms, some special equipments, how to handle the sulfides. Other one will be the polymers. The polymers are also interesting. They are mechanical flexible, so easy for manufacturing. But polymers are limited in the thermal stability and only stable up to 4 volts. So the high voltage system is not so easy to generate here, but it's very interesting for maybe for classical applications here. And we have oxides. Oxides are like ceramic materials. They shows also very high conductivities and they are also stable in air, so you can handle it here. But they are brittle and hard and so are difficult for process. So the question is here almost how we can make a real cell with these materials. So you need sintering and also think about the cost. So still now yet no optimal choice for the electrolyte due to different characteristics. It means so you have really to think what kind of application you would like to address and what kind of material could be the best choice for this. It should be very clear in mind what are the real improvements here. And in this slide, I would like to show you here some theoretical, or make some thinking, theoretical view about these technologies. And here's some calculations where we did to use a classical lithium-ion battery and just exchange the liquid electrolyte with the solid electrolyte. Here, so on the left side, you can see the calculation with a liquid electrolyte-based battery technology, which energy is around 250 watt-hour per kilogram. And now we did exchange this with a solid electrolyte, for example, with a ceramic or oxide. Here, for example, the garnet, the lithium lanthan, the conoxide system. But you can see in the first step, you will lose energy because the garnet is more heavier than a liquid. But the garnet is a very stable material, so you can use lithium metal as an anode. So you also came to the same level. But also, if you use a high voltage cathode, you will clearly improve the energy density with this kind of materials. So the most key message here should be, and keep in mind, if we exchange the liquid with a solid system, becoming more heavier, because the density from the oxide, it's higher than a liquid. And this is why we have this reduction in the energy here. But by using some other advantage, lithium metal or high voltage cathode, you can improve it. The same calculation was done with a polymer. Polymer electrolyte was used. And here you can see there's no change in this energy density. And this is due to the density of this polymer, which is similar to liquid. And if we have a polymer which could be also stable with lithium metal or also stable with a high voltage cathode, we can improve a lot the energy density of the system. Also given here with the volumetric energy density, they really a dramatic increasing here in this volumetric energy density. So it's a great opportunity, but the thing is here also you should keep in mind the processing, also how we handling the solid interfaces. The need of applied pressure is possible question. The safety issue is also a very important point because polymers could also be burning, it's depending, but it should be think about this, especially if you use lithium metal. And also the energy density should be much higher, but significant optimization has to be done because due to the question how to make the cells. About this of manufacturing process, we will get also a next webinar in webinar 3 about this. So I would like to give you this key message. So also state batteries are very attractive, but if you use the classical cathode materials, what I mentioned, the weight is much higher. So the solid electrolyte-based system is heavier. So we have to exchange lithium metal we have to use and the high voltage cathodes. So we come in cell level, or if we also make a thin electrolyte, also less amount of material here, we can really improve the energy density of this solid state battery technology. So the key message is here really the electrolyte density and the separator thickness have the most significant effect on the specific energy and energy density. So here should be really a smart design and process strategies necessary to reach really the maximum value of this technology. Finally, there's also an important view about the raw materials, what are used, and we have also next part in this webinar, also given by Gwen, more detailed information about this, but the materials that are used in the lithium-ion battery technologies are use lithium, nickel, cobalt, graphite, silicon, germanium. So these are mostly not in Germany available or Europe. So we are depending from other countries here, but also this will be need for alternative battery chemistry. It's really interesting to overcome these dependencies of other countries. And I would like to give you 3 view about here. Maybe one alternative will be the zinc-ion batteries. So the zinc-ion batteries are working in the principles the same like lithium-ion batteries, but here is not the lithium ion, so it's zinc ions was shuttling here between the anode and cathode. The zinc is very eco-friendly because we have also aqueous electrolyte we can use. It's very cheap, it's non-toxic, it's available, this material is abundant. They also showed very high cycle stability, 10,000 cycles is also shown in some publications about this, but it's a lower energy density because zinc is heavy compared to lithium, but it's a high power density. So this could be a very interesting technology, maybe for stationary applications, which is very cheap and also safe. Another kind of alternative what will be also in investigation is the sodium-ion batteries. Sodium-ion batteries are very interesting because this could be gets a similar energy density like lithium-ion batteries. Sodium is available a lot, much more, and also this technology have already commercialized, but have to be as a starting point now. Here there's some startup companies who try to get this in a product. It's also very interesting. It's cheap. You don't need copper here also because you don't use copper as a current collector. Here's aluminum is used. And also it's very interesting because there are excellent sodium-ion electrolytes or solid-state electrolytes available, which also is very interesting to realize all solid-state battery based on the sodium technology. This could be very interesting alternative due to the lithium-ion battery technology. You can see some picture here. There's some companies, Faradion or KTL, should claim to have these batteries here. And another kind of interesting technology are the lithium sulfur batteries. This is a difference here is that we have now how to say, this rocking chair technology, or it means this intercalation happens. So here we have lithium metal on one side, we have an organic electrolyte, and we have the sulfur, a pure sulfur as cathode. And the advantage here is the sulfur is very cheap. There's no problem here, but the reaction here is a little different in comparison to the lithium-ion technology. Here, so there are different kind of reaction happens, different kind of lithium sulfide products are there, which are dissolved here and will be also reduce the cycle stability. We call this reaction more as no intercalation, is a more conversion reaction here. So this is very critical to handle for long cycle stability. But it's very interesting because to the energy density, what you can see here, 2,600 watt-hour per kilogram, so it's much, much more. And it's very interesting. There are still now some prototypes are running, and the idea is maybe commercialization maybe in 10, 15 years ago. Good. And finally, the big step in the future will be the lithium air technology. It's metal air batteries, we call it here. Here is the difference that we use the oxygen from the atmosphere as a reaction product. So it means we have lithium as a metal anodes, we have an electrolyte here, which conducts lithium ions, and this could be react with oxygen. So we have lithium oxygen here as a reaction product. So here you can see it, and this is also possible, and you can compare it also with our general fuel. We have here the carbon from our fuels. We also burn it in our cars, maybe with oxygen, and we get CO2. And the CO2 is a gas-like system, and we blow it out in the atmosphere. And here's a similar one. It's a more electrochemical burning, but here this reaction product is a solid. So the lithium peroxide, what you can see, lithium oxide, what you can see here is a solid. And this means that the pores, what these are, will be closed during the discharging, and no oxygen can more migrate inside the electrodes here. So this is a very challenging thing, but also this reaction, what you can see in the middle, it's a very complex reaction with superoxides and peroxides, and these are so reactive that also degrades the electrolyte. So the question about here is what kind of electrolyte we can use here, what's about the oxygen solubility, and what's about the lithium oxide storage, because it's a solid. It's a very big view in the future. Some small developments was happened here, but still the question is here about what kind of electrolyte we can use, and also what is about the reversibility here in this case. Good. So this was a short view in the future about this. And Gwen, now you can.
Yeah, thanks, Julian. So we are now at our second discussion point. This time we would like to look at some of the challenges of the future battery market. It's the battery market and research is certainly experiencing a period of change. This provides us with opportunities to maybe do things differently, but it also provides a lot of challenges. So our question to you is, where do you see the challenges for the battery of the future? So I will give you a second or a minute or so to start gathering your thoughts and put in an answer here in our word cloud. To give you an idea of how this word cloud works, the answers that are present in a bigger font are basically appearing more often. You can also go and click on one of these words if you would like to confirm that that is also something that might be interesting by giving it a thumbs up. If we're looking at the word cloud for the answers that are coming up, it really seems that everybody thinks the most significant challenge is the raw materials. And this is going to be a great transition to our next section. Other aspects like materials or cost, recyclability keeps coming up, particularly in combination with, I saw that here, design for recycling, material scarcity. Of course, these can all go together. Recycling can provide a new resource. Down on the bottom at the moment, I see charging speed, which is now up a bit higher. A few other things in terms of technological issues. So charging, lifetime, the fire hazard, how to make batteries safer. These are all technological aspects that are certainly being addressed. There's a lot of talk about things like fast charging and so on. But really, it seems that the main challenge, at least coming out of this community or this webinar, is the aspect for raw materials. How can we secure raw materials for batteries? How can we reduce the impact of critical raw materials? And what other ways do we have to secure materials for battery technologies? And so maybe at this point, that's the right place to move on to the third section. So now we're going to talk about things with raw materials and moving in towards battery recycling. So this slide, Julian already showed, but basically the take-home message here is if we look at this graph, if we look at this world map, where are the materials for batteries coming? Very few are coming from Europe. Most of them are coming from areas like Asia. Of course, the most well-known example for batteries is cobalt coming from the Democratic Republic of Congo. But in general, there's very few resources available for batteries in Europe. And so this means that we do have, not only for critical raw materials, but basically, if you look through the list here, all of the materials associated with batteries are considered to have some sort of a supply risk, particularly cobalt, nickel, and lithium. Of course, lithium is coming primarily from South America. But if you look more closely, basically every material that you can put in a lithium-ion battery has some sort of supply risk. So things like phosphorus, which would be for LFP, natural graphite, fluorspar, which is used for all of the fluorinated compounds, silicon, manganese, aluminum, iron, copper. With these list of materials, basically, you have everything you need to make a lithium-ion battery. And so naturally, in the future, this is something that can provide a significant challenge, as we also saw in our last discussion. We need to secure the raw materials. So maybe to look at this a little more closely, particularly now in terms of the critical raw materials, this is the list provided by the EU, the latest update in 2020. And you see a lot of materials in general for important technological applications. But if you go through the list and compare that, as I mentioned, with the battery materials, you again see all of these critical resources. So the cobalt is clear. Fluorspar appears again. However, there's also things like the research materials used for solid-state batteries, indium with sulfides. Niobium is often used as a coating for cathodes in combination with sulfides. Tantalum with LZO, an oxide-based solid-state electrolyte. And then you can even start to see things that could possibly play a role for sodium-ion chemistry. So for example, vanadium, NVP or sodium vanadium phosphate is one of the sodium cathodes that's being investigated at the moment. Also here, vanadium for redox flow batteries. And so the point is, in general, raw materials are definitely an issue. Let's look now a little bit at the growth in the minerals required for batteries. So if you look at the graph on the left, basically you'll see here a percentage. What this percentage means is how much of demand in 2050 will there be only for low carbon technologies in comparison to the complete 2017 production. So for example, in the case of nickel, you see the amount projected to be needed for only low carbon technologies more or less surpasses everything that was produced in 2017. And nickel in this case is one of the smaller examples. Graphite, almost 400%, cobalt, 600%, and lithium, almost 1,000%. If you look more closely at where these materials are being used, so at the moment, or at least in 2017, only about 1% of the nickel being produced was going to battery demand. In the future, this is going to increase, and thus is definitely even more relevant in the case of lithium and in the case of cobalt. So this brings us to the question, how can we reduce the demand for materials from primary resources? So one is certainly in terms of extending the battery lifetime or repurposing batteries. So here the keyword is second life. And the second is then, of course, recovering the materials from spent batteries through recycling. So to give you an idea of the role that recycling could play in the future, lead acid is probably a good example of what could be done with a proper recycling program and a proper recovery of the materials. So what you see in the left in the bar graph is the end-of-life recycling input rate. This means the percentage of the raw materials needed that are coming from recycling processes. So if you look at lead, now I will try to also get my pointer here, you see about all of the lead, about 75% of the lead that is being needed for new technology is coming from recycling. So you might ask why this is why this is the case. But it's because there are very well established lead acid battery recycling programs. Of course, in the case of lead, this has to do with the toxicity of lead and ways to keep lead from going into the environment that initially got these programs to be established. But it has basically ended up with a more or less, I mean, not completely, but more or less a closed loop where the resources that are needed are coming from recycling. At the moment, the lithium-ion battery materials that are coming from recycling are largely limited to the valuable metals, so things like cobalt, nickel, and copper. As a comparison, I've put a graphic here of the different components of a lithium-ion battery and what percentage they make to kind of allow you to compare to what could come from the end-of-life recycling input rate. One of the keys to developing a good recycling program for LIBs will come through the new battery regulation that is being put together from the EU. So this new regulatory framework will set sustainability requirements. I'd like to pick out a couple of the points that are given in this new battery regulation. The first one deals with recycling efficiencies and the recovery of materials. So here, if you look on the top right, in terms of the option 3, the high level of ambition, when you're looking at a recycling efficiency for lithium-ion batteries, ideally 70%, or this could be the regulation, that 70% will have to be recycled by 2030. And in addition, they will be looking for material recovery rates for cobalt, lithium, and copper of 95% and lithium of 70%. In addition, if we look at the point 9, the recycled content in new industrial EV and automotive batteries, here there will be a mandatory level of recycled content that has to be included in new cells. These levels have not yet been defined. This is something that will have to come in the future, but it will mean that the materials do have to directly go back into lithium-ion batteries. So how does this look in terms of the recycling programs or the recycling of batteries that exists today? So you can see at the moment in 2020 or even by 2025, the kilotons of returned quantity will be rather low. And more interestingly, the amount or the materials are coming from, for example, 3C batteries. So 3C means computing, consumer and communication applications, and also from production scrap. So here the two grays, the light gray and the dark gray, are both cell and pack production. It's expected that the returned quantity, of course, is going to greatly increase in the coming years, from the minimum scenario to the maximum scenario. But in terms of having a really large volume of batteries, recycled batteries, really you're looking at a delay of about 10 years where you're starting to see the batteries that are coming back from automotive applications. So represented here by the large blue bars. So now, what do we do with end-of-life batteries? First of all, what is end-of-life? So the generally accepted definition for the primary use is when 80% of the total usable battery capacity remains. After that, so when batteries have come to the end of their first or primary use end of life, then this is where the discussion of secondary use comes into play, or most well known as second life. However, at the end of second life, then of course batteries are going to go into the recycling chain. And there's a number of different ways in which the batteries can come into the recycling chain based upon the different type of recycling process that can be used. So Europe at the moment is emerging as one of the hotspots for battery recycling, along with North America. You can see a variety of different countries distributed throughout Europe that are working on recycling or have industrial processes being developed or already in place for battery recycling. Most of these industrial processes at the moment are based on either pyrometallurgical or hydrometallurgical recycling processes. Although at the moment, you're starting to see more companies that are looking at a combination of both. So there's three basic processes that can be used for battery recycling. The pyrometallurgical process here, which is practically the largest loop. What this means, I'll look at in a minute on the next slide. The hydrometallurgical process, which is a little bit of a smaller loop. And then finally, the concept of direct recycling, which basically is going to give materials back in a form where they can be directly put into battery recycling. But we'll look at that as well. Okay, so when you compare the different types of recycling, more or less the differences have to do with the types of materials you can get back, but primarily through economical means, and at what point in the value chain those materials enter the battery manufacturing loop. So if you're looking at pyrometallurgical recycling here in the top circle, you see that for cobalt, nickel, and copper, this is particularly economical. There are other materials like graphite and aluminum that can't be recovered. And basically what you get out at the end of the processes goes back into the smelting process to make the alloys, and then goes into the process of making materials, which can then be used to make the battery cathodes. When you're looking at a hydrometallurgical process, now you see a few more materials have become economical. In addition, you can see basically all of the materials can be recovered. And what you produce in the end is the chemical compounds that can then be directly used to make new cathodes. And the shortest loop, or the smallest circle in a sense, is the concept of direct recycling. And here, the idea is not to decompose the materials themselves so that you resynthesize new materials, but rather so that you can recover the materials themselves. On the right, you can see a comparison in a spider diagram. So in the middle is the worst scenario, and the outer part is the best. And here you can see the advantages and disadvantages of the various different processes. So in terms of pyrometallurgy, you see that the processing simplicity and cost is a big advantage. However, you see that there are particular challenges in terms of the environmental impact. In hydrometallurgy, the big advantage is the product quality here. And finally, for direct recycling, you're seeing that you have a completely closed recycling loop. It is projected to have a relatively small environmental impact. And so it provides certain advantages compared to these other two processes. So specifically, what could direct recycling look like in the future? So this process is currently in the R&D stage, and therefore the optimal process chain is still under investigation. And as a part of this, there's a lot of different direct recycling processes or routes that you could envision, and these will likely depend on what cell chemistry is being recycled and which technological solutions are the best for each particular step. In general, one thing to point out about direct recycling is it will probably be rather important to do a pre-sorting step of the batteries. And here this would be tie back to the concept of a battery passport, where all of the relevant information about a particular battery can directly be read from some sort of technology that is present either on or within the cell. The direct recycling will certainly be facilitated by design for recycling concepts. So what does that mean? It means concepts that are designed now will be integrated into the manufacturing of new lithium-ion cells that will then facilitate the recycling at a later point. In general, direct recycling provides possibilities for cost and environmental savings. And this is really an opportunity, I think, I think because we spend a lot of time at ISC working on this, for new recycling positioning, for example, in the European industry. And so with that, I will hand back to you, Julian.
Yeah. Thank you very much, Gwen, for interesting introduction or short overview about the battery recycling. So now we would like to know from you about your opinion. Maybe the question will be, battery recycling is currently in a period of developments and rapid growth. What opportunities do you see in the battery recycling? So maybe is it a costs, or is it an independency? Maybe could be also be a new kind of business developments in this case. What do you think about what kind of opportunities are there in view of recycling? Is this also the local strengths of the economics? I see raw materials are very important about this, but also interdependencies is very important. Costs are also very important, right? So how do you see? It's very interesting also to see, geopolitical advantages, very important. I think here also maybe now in this new kind of developments in our political global situations. Value chains, very interesting. Also the better for environments, right? Excellent. So I see a lot of ideas here. So I think the raw materials independency is a very important point. Also, new kind of business developments. It's very interesting to see here. Our circular economic, I think, getting more stronger in this case. And I see the biggest one is the interdependency, what you are thinking. I think it's a really wide way. Okay, then I think circular economic, this is a key word about this, about recycling, to reuse all. Then thank you very much for your opinion. So I think now we have time for some discussions, right?
Maybe we will shift over to Mikkel to wrap up the formal part of the seminar or the webinar.
Yes, I will close the session for today. So thank you, Gwen, and thank you, Julian, for your interesting presentations and your given insights in the material cycle of lithium-ion batteries. And also a great thanks to the huge number of interested participants today. Due to small technical problems, we are a little bit over time, but we now reached the end of our lecture and we'll stop the recording. And right after, we start with the casual Q&A with our two experts for further discussions. So yeah, once again, and finally, I'd like to leave my recommendation to check out our website for all future events and learning opportunities. The registration for the webinar sessions 3 and 4 are already opened, and also the pre-registration for the pre-charger workshops is possible. So hopefully we will see you again in spring 2023. And now, thanks again for your interest and a good day to all of you. For all those who are interested, please stay in the line, and we are going right after in the Q&A and discussion session. Thank you.